Okay, so now we're recorded. So I mean, this is it's a topics class. So, I mean, usually when we teach these classes, it's very all in person, and we'll get to know each other. And the goal of this class is to be sort of interactive, and we have discussions. So I'm thinking, suppose it would be nice if you could just have the videos on during class. I mean, if you want to, I mean, it'll just make it feel like more like a class. I mean, more not just Max lecturing, but actually having a discussion here. So it's nice if people can have the videos on. And also, I think it might be good if people could just start with a short round of introductions. I mean, it's a relatively small class. I mean, I think it would be nice if we all know each other. So I don't know, people could just go in order and introduce themselves. Any order.
Order is always hard with Zoom, but I guess it makes sense for me to start just because I'm the TA/contractor. So I'm Max. Hi, if I haven't met you. I'm a PhD student in the theory group, working with Shachar and Daniel on high-dimensional expanders and other stuff. And I'm looking forward to the course.
Yeah.
Hello, everyone. I'm Nicholas Seeger. I'm a third-year PhD student in the math department, working with Sam Buss and Ban Chung. And I definitely wanted to see what all this stuff about high-dimensional expanders is all about.
Hi, everyone. I'm Gaurav. I work with Shahar and Sanjay on learning problems, and I'm very excited to learn about expanders too.
Hi, I'm Michael. I finished my undergrad here like about a week ago, but I'm interested in combinatorics and theoretical computer science, so I'm here to learn about expanders.
I'm Anthony. I'm going to be attending UCSD in the fall for graduate studies, and I wanted to get a little bit of a head start by learning about high dimensional expanders and the kind of state of the art in that field.
Taking time to people. I mean, maybe we could just say by order what we've seen here.
Hey guys.
Yeah.
Hey, I'm an undergrad at UCSD, and I'm just exploring like different TCS areas for because I want to do my PhD in TCS mostly, so that's why I'm attending this class. And yeah.
I see we have Ashwin here. Ashwin, you want to introduce yourself?
Third year in EC department. I'm working with Harris Story.
Jean Long.
Hi everyone, I'm PhD student in physics department. I'm working on quantum information and quantum computations. So I'm looking forward to see how the high dimensional expanders can be applied to the quantum error correction code.
Oh, Kartika.
Hi, I'm Kartika. I'm a second year master's student, and I'm looking forward to learning about high dimensional expanders.
Zoom keep changing the order here. I guess medicine.
Hi, I'm a PhD student in EC. I'm taking the class because I'm interested in the applications to error correcting codes that can be represented by expander graphs.
Okay, perfect. Xiaowei.
Oh yes, hi everyone, I'm Xiaowei, and I'm a second year CSC student. And yeah, the course name is really attracting me a lot because I know nothing about high dimension expanders. So I just want to learn a lot about this. Thanks. Yeah.
Hopefully by the end of the quarter, you know something. Yubo. Okay. Chutong.
Hi, I'm a first year master student. Yeah, I'm also interested in the topic expander and hopefully have a wonderful quarter. Thanks.
Henwen.
Hi, I'm a third year PhD student. I'm interested in combinatorics and graph theory in general. Hope I can learn something in this course. Thank you.
Right. Laura.
I'm a PhD student. I work on cryptography. I'm just interested in the topic.
Mohit. I don't think Mohit spoke it, right?
Hey, I'm undergrad studying math and CS. I'm broadly interested in pseudo randomness, and yeah, I'm just interested to learn more about this topic.
Pawan.
Hi, I'm Pavan. I'm a third year undergrad, and I'm interested in this class because I really enjoy graph theory, and I'm interested in learning about the specific set of graphs as well.
Okay, great. Richard.
Hi, I'm Richard. I'm a fourth year undergrad, and I'm interested in learning how expanders connect to other areas of mathematics.
Okay. I'm not sure if I missed anybody or not. Again, Zoom keeps changing the order for me, so it's hard to see if I missed. So if I missed anybody, then please introduce yourself.
Hi, I'm Shubham. I'm a first year undergrad math CS major. So I just wanted to take this class because I took extremal combinatorics, so I thought this would be a fun thing to try to.
Great. Anybody else that I missed?
Oh, hi everyone. I'm William. I'm a fourth year undergraduate. I also really enjoy combinatorics after taking extremal graph theory, and so I wanted to learn more about expanders. Yeah.
Excellent. Anyone else? Okay, so hopefully we didn't miss anybody. Yeah, perfect. So maybe just before we start, let's just go a bit about the logistics of this class. I mean, what you see, this is an online class. I mean, that's obvious. I mean, we have a website that I hope you all saw because, I mean, you needed it with the Zoom information, but it contains all of the information about the class. Let me just quickly go through it just to explain a few things. So yeah, so basically, so Max and I are going to be co-teaching this class. The classes are Tuesday, Thursday, 11 to 12:20 on this Zoom. We are going to have office hours. I mean, during the week, we still need to set them up. So stay tuned for that. And we're going to use the same Zoom link for the office hours. So it should be easy. Evaluation is homework and a final project. So we're going to have, I think, about 4 or 5 sets of homeworks. And you can do them either individually or in pairs. That's up to you. It could be the same pairs, different pairs. You can alternate. It's up to whatever you want. And similarly for the final project. So either individually or in pairs. And then we have a tentative schedule here that we set up. Again, it's tentative because we're still working on preparing all the material. And but that's like a rough sketch of what we're going to cover. So the first 5 weeks, we are going to cover what is more, let's say, classic material in expander graphs. So it's material that we have been studying and using for the last probably 40, 50 years. I'm sorry, 1 second. My dog was bugging me to get up. So that's the first 5 weeks, and then the second 5 weeks, so weeks 6 to 10, it's going to be more about high dimension expander, which is a much more, say, recent emerging topic that is sort of still being investigated to a large extent. I mean, so we'll cover the basics aspects of it, but there's much more material that we can cover. But it's going to be a good starting point for people that are interested in high dimension expander, at least to get some sense of what they are, what can they be used for, how can we study them, in what ways do they generalize expander graphs, and then of course there are many other places to go after that. And we are preparing lecture notes that's going to accompany all of the lectures. And we'll work with it. It's work in progress. I mean, so I put instructions here how to see, instead of just putting here a PDF of keep updating it, we just gave you access to the overlay. So we're actually creating these notes and you can just download the PDF. So there are instructions here. So just click on this overlay thing. By the way, I don't know what you see. So do you see the overlay loading?
Yep.
Yeah. They go here and it's read only. I mean, for me, it's not read only because I'm the host, but for you, it's going to be read only. And to download, you click this icon here, this arrow with box, and then just going to download the most recent version. Okay, so hopefully that should be easy. And again, because this is sort of work in progress, so these notes are going to keep changing. But I think the notes for the first 3 weeks are more or less stable. So weeks 4 and 5 are still in progress, and HDX we haven't started yet. But weeks 1, 2, 3 should be more or less ready. If you find any mistakes, any typos, if it's not clear, please let us know. Again, the goal is that by the end of the quarter to have this set of notes that could be useful for other people as well who want to study this material. With that's part of our goals. And also I listed here at the bottom a bunch of other links for material that might be useful for you. So it's a class on high-dimensional expander that you already taught a few years ago, and then a survey paper on expander graphs. That's actually going to be the basis of everything, or most of what we're going to cover about expander graphs. We'll cover some of it, not all of it. And then there's another lecture by Avi Vigdorzon on expanders and a survey, more an algebraic survey on high-dimensional expanders by Alex Lobotsky. So I mean, this might be useful for some of you, maybe for the final project, or for if you're interested in some specific aspect that we're not going to cover here, so just so you have this information. So I mean, one thing that's, let's say, lacking about high-dimensional expanders is that there is no good survey or book out there. This is too much of a recent area, recent topic. So there's one survey by Lubotsky and classes and lectures, but there's no one body of work that you just read and learn about it. And that's just a reality of this being like a much more recent emerging topic. On expanders, it's a much more classic topic. There are very good books, and like this book by Huri, Lidner, and Vigdon is a really good book. It doesn't cover everything. It covers many of the developments, and then there are other surveys that cover more things. So this is much more of a developed topic. So any questions on logistics before we start with the material of today?
For the final project, is like what it is already crystallized, or will we get information like
we haven't fully decided yet, but one possibility would be that you choose some area that is related either to expanders or high-dimensional expanders that we didn't cover in class, and you read about it and you write a survey about this area. So it could be about some area you're interested in. Maybe it's how you use high-dimensional expanders to build quantum codes, or how you use expanders to build resilient networks, or whatever. There are many other areas, right? Connections to topology, connections with many different things. So it's much more open-ended. And this way, I think everybody can just choose whichever area they're interested in, so dig deeper into it. And then, of course, these things could even lead later on to more research-oriented projects. It could be a good starting point for that. Or people interested in research in this area. Okay, any more questions on the logistics? Okay, perfect. So let me stop sharing that and start with the material. So, I mean, ideally, we would teach this using a whiteboard, but since we don't have a whiteboard, so I'm just using my iPad, which is a poor substitute, but this is what we have. Okay. second. Good. So expanders. Okay, so what are expanders? So expanders are graphs. So I'm assuming that you all know what graphs are. You know, we have nodes, we have edges, and you know. Okay. So we have nodes, and we have edges in between the nodes, right? So we usually don't graphs by VE, where V is a set of vertices and E is a set of edges. And you know, in this class, unless we say these are all going to be undirected graphs, they're all going to be undirected. And no loops. Okay, so just simple graphs. Okay. And now what the whole idea of expanders is that you want graphs that on the one hand are sparse, so that they don't have many edges, but on the other hand, they're very tightly connected. So we're going to today see several definitions of what does it mean for graphs to be highly connected. And then what we're going to do is spend the next few weeks studying how are these notions connected to each other and what applications can they have. And then later on we'll discuss also constructions of such graphs. So, but first things first, let's start with some definitions. So we're going to start with some more combinatorial definitions of expansion, because that will be the one that are maybe the more natural one, the easiest one to explain. So first, let me make some definitions. So here's a definition. So I have ST, which are subsets of nodes. So I'll denote the edge set between S and T to be all the edges that have a scope from S to T. Okay, and even though the graph is undirected, it will be convenient to look on edges that are directed, going the first node being in S and the second one being in T. Just to write this formally, it's going to be the set of all tuples ST. So S is a node in S, T is in T, and this edge ST is an edge, right? Okay, this just will be a useful notation. And then we're going to define the notion of a boundary of a set. So for example, when we discuss two things, we discuss edge boundary and vertex boundary. Let me start with edge boundary. The definition also. So the edge boundary of some set S of nodes is the following thing. It's the edges that go from S to the complement of S. So for example, if this is my graph, let's just draw some graph here. This is my graph. And my set S happens to be, I don't know. This is a set S. The edge boundaries are all the edges that have one endpoint in S and the other point outside S. It's going to be this edge and this edge and this edge and this edge. Okay. So that's the edge boundary. And we're going to use usually we just denote it by what's called the boundary of S. So that's going to be the way we denote it. And so that's going to be counting, given a set of S, how many edges it sees going outside the set S. We will also talk about vertex boundary. Which is going to be the set of vertices that are adjacent to node in S. So we're going to make neighbors of S. That's going to be all these nodes V that are not in S, such as there exists U in S, where the edge UV is in E. All right, so for example, here, this would be maybe different color green. This would be, I guess, all these nodes, but they all have edges to this blue set. But of course, if I had this other node, this would not be part of the vertex boundary. Okay, so again, two definitions, two combinatorial definitions, asking given a set of nodes, how much it expands out. Edge boundary talks about edge expansion. So how many edges go from this set to outside the set. And vertex boundary talks about vertex expansion. How many vertices, new vertices can I reach from this set? Go and take it one step in this graph. Okay, and we're going to use these two definitions to define two combinatorial definitions of expansions. Edge expansion corresponding to edge boundary, and vertex expansion corresponding to vertex boundary. So, but before I define them, are there any questions on these two definitions, edge boundary and vertex boundary, of a set of nodes in the graph? Okay. So now let's define expanders. Okay. So now we're going to define expanders. So we're going to define two types of expanders: edge expanders, edge expansion. So let's say I'm just going to follow the same as in the note. So a graph G VE is an epsilon edge expander. So I'm going to use exp for expander. So keep putting expander as exp. We put it as expander. Expander if for every set of nodes of size at most v over 2. So I'll explain why v over 2 is natural here, but just take it for now. So satisfy the following thing. So let's define h of s, which is the edge expansion, the fraction of edges that leave S. Let's just write this way. So I'll write it and explain. Okay. What do we have here? So let's first look what h of S is. H of S, remember that this boundary of S, this edge boundary of S, counts how many edges go from S to outside S. Okay. What is ESV? Well, that's a total number of edges that go from S anywhere. So this ratio is just a fraction of edges going from S to outside S. Or in other words, if I choose a random node in S and I take a random edge leaving it, what is the probability that this edge is going to go from S to outside S, right? Going to escape S. Right? This we denote by H of S. This is the edge expansion of a set S, or the fractional one. And what we want is that all these sets have some non-trivial edge expansion. At least an epsilon fraction of the edges leave this set. And okay, so why do we have this condition of S being at most size v over 2? Because really what we look here is on cuts in a graph, right? So here's an equivalent way of thinking about it. So I have a graph, use a different color here. So here's my graph G. And I break it into two parts, S, and let's say S complement, right? So S complement is just a shorthand for V minus S. So the other nodes. And what we really want to measure, say that every such set should have many edges going between the two parts. But how do we define many edges? Well, with respect to the smaller parts, right? Because we have a large part and a small part in every cut. Now, it doesn't make sense that there will be where we compare the number of edges to the number of edges in the large part, because that could be a very large number, right? Imagine S is just a single node. So there will be some small number of edges leaving it. But what we wanted is to compare it to all the possible edges leaving the smaller of the two parts, which is why we're assuming that S has size at most v over 2. So then take any cut, S and S complement, and then assume that S is the smaller of the two parts, or maybe not n over, most n over 2 nodes. And what we want that this set, or the cut in this set, is going to have many edges crossing this cut, going from S to S complement. We call this H of S. This is the edge expansion of S, and we want this to be at least epsilon for all sets S. Okay. So this is the definition of an edge expansion, and we're going to see an example very soon. But before I want to show the example, I want to also define vertex expansion in a very similar way. So the vertex expansion so again, so G VE is an epsilon vertex expander, sorry, an epsilon vertex expander if again the same thing, but now we're not going to look on edge expansion, we're going to look on vertex expansion. So the number of neighbors of S, and now it makes sense to normalize by the size of S, is at least epsilon. Okay. So again, these are the two main definitions that we're going to talk about today: edge expansion and vertex expansion. So a graph is an epsilon edge expander if any set of it's small enough, at most half the nodes, at least an epsilon fraction of the edges, that if you started this set, you're going to go outside the set S. And the graph is an epsilon vertex expander if the same thing holds for vertices. If I choose any set of S nodes and ask, well, how many new vertices can I see by taking one step in this graph? Is at least an epsilon fraction of the original set of nodes. Okay. So let's see two examples now. Hopefully, would clarify these two definitions. But maybe before that, are there any questions about the definitions, about notation or anything? I mean, even if it's not intuitively clear, it's fine. But I mean, at least I want you to see if you can understand the notation here before we see some examples. Okay, so let's look at some examples. So actually, so here's a very interesting example, which is the complete graph. So take the complete graph. No, Km. So it's n nodes and all the possible edges. So no, complete graph should be very, very, very connected. So we expect to be a very good expander, both in terms of edges and in terms of vertices. So I claim that the complete graph is going to be a half edge expander and the one vertex expander. So the larger these values are, the better it is. So why half edge expander? Because if I take a set of n over 2 nodes and ask what's the probability that a random edge starting this set goes outside, it's going to be half. And if it is smaller than half, it's going to be even bigger than half, right? So usually for a complete graph, the set that expands the least, you take exactly half the nodes. And then half the edges go out. And again, the number of new nodes you're going to see is at least as much as the amount of nodes you started from. So this is something that maybe you can just, it's good for you to verify for yourself, after the class, that you understand the definitions. So the complete graph is a very good expander. In fact, you can prove that's the best you can hope to get. So there is no graph which is better than a half edge expander or better than a one vertex expander. But the complete graph has one problem. It's very, very, very dense. It has all the possible edges. So really our main goal will be to study sparse graphs. Graph has very few edges. That are still epsilon, edge or vertex expanders. And we're going to say that such graphs, first of all, have connections to interesting phenomena in mathematics, in particular in algebra, and also in combinatorics, but also they have many interesting applications. For example, the best error correcting codes we know how to generate are based on these graphs. We can build resilient networks based on these graphs. We can build efficient error reduction in algorithms based on these graphs. So many, many applications are based on having these graphs being very, very sparse. And now for the most part, we're going to talk about regular graphs. That's because it's going to simplify, a lot of the calculations, and because all the constructions, all the natural ones are going to be regular anyways. So I'm going to assume that, our graphs is going to have the following thing. I'm going to assume it has n nodes, and they're going to be d-regular. So d-regular means that all the nodes, so all the degrees are d. Right, so every node has degree d. And ideally, what we want is d to be a constant. Right? The smaller d is, the sparser the graph. So the next example I want to show you is for a very, very, very sparse graph, which is an expander. So this is going to be another example. And this example is something that we call the cycle graph. I mean, it has different names, but I'll call it a cycle graph for now. So I'm going to choose, let's choose P to be a prime. So the vertices are going to be ZP, I mean, all the numbers modulo P, 0, 1, up to P minus 1. And the edges are going to be of the following form: x plus 1, x minus 1, I mean, that's going to be just a cycle, and x 1 over x. Well, just here, I want to point out that I'm going to define 1 over 0 to be 0, just for convenience. I mean, there are other ways to do it, but let's just do it now this way, just for simplicity. So what was it? So how is this graph? What does this graph look like? So let's say we're going to choose P to be 7. That's going to have 7 nodes. 1, 2, 3, 4, 5, 6, 7. Let's give them names. 0, 1, 2, 3, 4, 5, 6. First, we're going to create a cycle between them. This is a plus 1 and minus 1. Okay. Notice this is a very bad expander. If I didn't have this 1 over x, a cycle is a very bad expander because, let's take, for example, half the nodes that follow here. This is going to have half the nodes, but only have 2 edges coming out of it. And only 2 nodes come. So a cycle is a very bad edge expander, a very bad, vertex or edge expander. But we want to add shortcuts to it. And turn out that adding this 1 over x is a very good way of adding shortcuts. So let me just try to erase this. So this 1 over x is this. We're going to say, what is 1 over x? Well, we said 1 over 0 is going to be 0. 1 over 1 is 1. 1 over 2 is what? 1 over 2 is, I guess, what is a half modulo 7? 4, I guess. Yeah. And then 6 maps to itself, and 3 maps to 5, right? Unless I made a mistake. So that's, well, this doesn't look quite like an expander, but if I choose P to be a large prime, then turn out adding this 1 over x is really a good way of creating shortcuts and making this graph to be very highly connected. So this is like a great expander. The proof that it is an expander is actually very, very difficult. So this was one of the first expanders constructed in algebra by Margulis. And the proof is based on a deep theorem in a number theory called the Selberg 316 theorem, and related stuff called Kashdan property T's, and I mean many topics that we're not going to cover in this lecture, or this class in general. But you should know that these constructions have a lot of deep connections and interesting connections to number theory, to algebra, and to other areas. We're going to see a proof of something similar like that later on in the class, around I think week 4 or 5. We're going to have a similar algebraic definition, but the proof is going to be more elementary. For now, let me tell you about another class of expanders that turn out to be very, very useful. And also you can also view this graph in this way, which is called Cayley graphs. So Cayley graphs is a way of constructing algebraic graphs. That is usually a very useful thing to do. So we're going to find, it's going to be based on a group. So let's H be some group. I mean, usually we use G to denote a group, but G here is a graph, and we're using H for a group. And S to be some subset of H. And the graph, the Cayley graph, HS is a following graph. So its vertex set is just going to be the group, all the group elements. And the edges are going to be all the pairs, let's say H, HS, H in H, S in S. Okay, so just all the edges you can get by starting from a group element in the group and multiplying by some element from the set S. Okay, this is in general, this doesn't have to be an undirected graph, but if we force that S inverse equals S, I mean every element in S is inverse is also in S, then if this is true, then the graph is undirected, which is what we want. So we just want to make sure that every element S we choose in the set S, this is called the generators, the Kelly graph. Then its inverse is also there. If you can go on an edge, you can also go back. So really studying these Kelly graphs is basically, if some of you know about studying word questions in groups, this is a very related object. Because taking a path in this graph is the same as multiplying by different elements from the set S, which is basically a word in the elements of S. But anyways, many graphs that we're going to see are Kelly graphs, and also this graph we saw here can be viewed as basically some generalization called Schreier graphs, but again, Kelly graphs are good enough for us for now. Let me give you one example of a Kelly graph that is not sparse, it is dense, but it's still going to be a good expander, but it's slightly less dense than the complete graph. It's called a Paley graph. So here's another example. It's called a Paley graph. So again, we're going to choose P to be prime. And we're going to choose the graph to be, the vertices is just going to be ZP. So all the elements in ZP. And the edges are going to be all the pairs X and X, Y squared. So Y is an element, the group. ZP star. So not allowing 0. So I'm allowing to multiply X by any square. Right, so all the edges correspond. This is basically the same as the Cayley graph of ZP with something that's called the set S, where S is a set of all Y squared, so Y is not 0. Okay, so this is going to be the number of squares in a group is roughly half the element. So this is still a pretty dense graph, but it doesn't have all the possible edges, only half the possible edges, and you can prove. And actually, we might see some part of it later, is that this, so its edge expansion, this is very close to half. It's actually half minus order of 1 over root p. So it is very close. As p is large, it's half is the best you can get. It's very close to half. But on the other hand, it's very dense. So it doesn't really help us. But just an example of a Cayley graph. This is an expander. We're going to see later examples of very sparse Cayley graphs of constant degree. So the set S is of constant side, which are good expanders. So here are some examples. So again, just to recap what we said so far, so we had these definitions of expansion that were combinatorial, talking about either edge expansion or vertex expansion. A graph is an epsilon edge expander if every small enough set has at least an epsilon fraction of the edges go out of it. And it is an epsilon vertex expander if the same holds for vertices. Every set has at least an epsilon fraction of new nodes coming out of it. And then we saw some examples of the things based on algebra, but the complete graph, and so on. By the way, here's a very bad expander, taking a disconnected graph, right? If my graph is disconnected, then intuitively it should not be an expander, and in fact it's not, right? Because if I choose, for example, one of the small sides to be S, then of course there's no edges coming out of it, no new nodes coming out of it, so that's going to be a zero edge or a vertex expander. That's a very bad expander. So if having an epsilon instead of 0 means you're very far from disconnect. You're in some sense robustly, not robustly connected. And we're going to see different ways in which this is actually, can be quantified. So any questions so far?
On the Paley graphs, I've seen these usually defined additively in the, like this would be x goes to x plus y squared. Does this make any difference?
I think you are correct. Yes, my mistake. You are correct. It should be plus. My mistake. Yes. Thank you. Okay, good. So now we're going to move into a different way we can define expansion that may be less intuitive, but turns out to be very, very useful technically, which is what's called the spectral notion of expansion. Okay, so now we're going to move to a new topic. Again, it's going to use linear algebra to define expansion, and it turns out this using linear algebra would be extremely, extremely useful to study expansion. So this is called spectral expansion. But before I define it, I want to first do a quick recap of linear algebra and some linear algebra facts that we will need when we study, graphs. So first of all, we can view graphs as matrices. So there's this adjacency matrix of the graph corresponding to all the edges. And for us, it will be more convenient to look at something called the normalized adjacency matrix, where we normalize by the degree. So let me just define it. So let G be a D-regular graph. Remember, all our graphs are going to be D-regular. So the adjacency matrix of G, the normalized one, is going to be the following matrix. So it's going to be a V by V. So G is V. It's going to be a V by V matrix, but I'm going to write it like that, so like UV. So this is like the row U and column V of this matrix. And it's going to define it the following way. If UV are an edge, I'm going to put 1 over D here. And otherwise, if UV are not an edge, I'm going to put 0. So for example, if my graph is this graph, this is not 2 regular graph, so this is 2 regular. So if I just give these things numbers, 1, 2, 3, 4, it's going to be a 4 by 4 matrix. And it's going to be 0 in all places except the place I'm going to write. So that rows 1, 2, 3, 4, and columns 1, 2, 3, 4. So this edge 1, 2 is going to be a half here and a half here. And this edge 2, 4 is going to be a half here and a half here. And the edge 3, 4 is going to be a half here and a half here. And the edge 3, 1 is going to be half here and half here. Okay. And all the other entries are 0. Right? It's going to be 0, 0, 0, 0. Okay, so this is what's called so if I didn't divide by D or by 2 here, this will just be called the adjacency matrix of the graph. But for us, it will be convenient to just divide by the degree. And you can define things also for non-regular graphs, but let's not do it because it doesn't really bias anyway. Okay, so we have this adjacency matrix. And then what we're going to study are the eigenvalues and eigenvectors of this adjacency matrix. So just a reminder, if A is an n by n symmetric matrix, then it has eigenvectors v1 up to vn that are linearly independent and eigenvalues corresponding to them, lambda 1 up to lambda n, and such that the following thing is true. So 1 is that no, v1 up to vn are in orthonormal basis. For Rn. So just now n vectors linearly independent and orthogonal to each other. Okay, and we're just going to normalize the unit length. And being eigenvalues means that A times Vi is lambda I Vi. Okay. So again, I'm assuming that, all of you have taken at some point a class on linear algebra, but maybe you sort of haven't used it for a while. So this is just these are the only basic thing we need about from linear algebra. That any symmetric matrix has a way of creating eigenvectors, and eigenvalues correspond to them, where the eigenvectors form an orthonormal basis, and A times Vi is lambda I. Just multiply with Vi, just change by a scalar. Okay. And in particular, our matrix AG is not just AG is a symmetric matrix, because UV and VU have the same value because the graph is undirected. So everything we said applies for AG, but also it is non-negative, and the rows and the columns sum to 1. Right? So that's going to have additional properties. So for AG, we also have that let's say we sort the eigenvalues so that lambda 1 is the largest one, then lambda 2, and then lambda n. That's going to be convenient to sort the eigenvalues in this order. So the largest one is at most 1, and actually the largest one is going to be 1 here, and the smallest one is going to be at most -1. So if you have a matrix where all the rows and the columns sum to 1, and it's non-negative, then you can prove, and maybe give it in the homework, that all the eigenvalues will be between -1 and 1. And in fact, the first eigenvalue is 1, and it corresponds to the first eigenvector, which is going to be 1, 1. But this is not normalized, so we need to normalize it with 1 of the root n. So this is 1 of the root n, just so this is going to be a unit vector. It has length 1. And the all 1 vector, so you can check that if you take the all 1 vector and you multiply it by the adjacency matrix, because this is the way we normalized by D, then we again get the all 1 vector, right? It doesn't change because every node has degree D. Okay? So these are all the facts that we need to know about in algebra, and again, they're all also summarized in the notes. So if you forget what we said, you can always go back to the notes and see what we covered. So now let's see how we're going to use this to define spectral expansion. Good. So notice lambda 1 is always 1. So we'll define actually 2 notions of spectral expansion. So we say G is a lambda spectral expansion if both lambda 2 and lambda n are not very close to the boundaries 1 and -1. And concretely, if the maximum of lambda 2 in absolute value, lambda n in absolute value is at most lambda. So what does this mean? It means that if you look on the eigenvalues, this is the interval between -1 and 1. So here's where all the eigenvalues live. And let's say here is 0. Here is 0. So all the eigenvalues are bounded in some interval between lambda and -lambda, except for what's called the trivial eigenvalue, which is 1. We're always going to have an eigenvalue 1. But all the other ones are going to be very close to 0, between lambda and -lambda. Okay? So we're going to see that having this property is extremely useful. And it is connected to both edge and vertex expansion. Okay? At this point, it shouldn't be clear why, but you will see why later. We're also going to have another definition that we're going to talk about. It's going to become more relevant when we get to high-dimensional expanders in the second part of this class, which is a one-sided definition. So we say G is a one-sided lambda expander if we just ask lambda 2 to be at most lambda. So we don't care about the smallest eigenvalue, we only care about the largest one. So pictorially, it looks like that. This is -1, this is 1, this is 0. So all the eigenvalues here, we allow for more. They can go all the way from -1 to lambda, and then the trivial one at 1. Right? So we allow for more. So one-sided notions are weaker, but sometimes they're enough. And sometimes this is all that we can get. This is also called having, this is also called having a lambda spectral. So the gap between one and the next one. Or in fact, sometimes 1 minus lambda spectral gap, but doesn't really matter. So again, the two notions are this stronger notion of bounding all the non-trivial eigenvalues, all except the first one, being very, very close to 0, absolute value at most lambda. And this weaker one-sided notion, just saying they're not very close to 1. But we don't mind about them being very close to -1. So what are the, let's just do some examples. Let's see 2 examples. So again, the complete graph. Well, what are the eigenvalues of the complete graph? Well, let's see, what is the complete graph? The complete graph, what's the adjacency matrix of it? It's going to be, well, it's going to be 1 over, let's say it had n nodes. So it has degree n minus 1. And then we're going to see here whether the diagonal is going to be 0 and everything else is going to be 1. Right? That's it. Right. Without this 1 over n minus 1, it's just the non-normalized adjacency matrix, a standard one. And then we divide by the degree n minus 1. How can we analyze the eigenvalues of this matrix? Well, it's the same. I'm going to claim as 1 over n minus 1, j minus I, where I is the identity matrix and j is the all one matrix. Right? I take the all one and remove the diagonal. Now j and I are commuting matrices, well, because I commute with anything. So they share an eigen vector space. And what are the eigenvalues? Well, j is an all one matrix, it has rank 1. So the eigenvalues of this, well, the all one matrix has eigenvalue n, but then all the rest are going to be 0. Right? All one matrix, multiplied by all one, I get the all one times n, otherwise I get 0. What is all I? I has eigenvalues 1, 1, 1, so just identity matrix. So overall, we get that the eigenvalues of AG are, so we need to subtract the 2 and divide by a minus 1 to be 1, and then minus 1 over n minus 1 minus 1 over n minus 1. So it is going to be a lambda spectral expander for lambda being 1 over n minus 1. Lambda being really, really, really close to 0. See, the larger I take n, the smaller lambda becomes. Right? So the complete graph is also a very good spectral expander. All the eigenvalues are going to be either 1, the trivial one, or minus 1 over n minus 1. Really, really close to 0. Now here's another example that I'm not going to analyze now, but if I take a bipartite graph, here's another example. I'm going to leave this as homework. If G is, let's say, K and N, so this is going to be the complete bipartite graph with n nodes at each side. So I have n nodes here and n nodes here and all the possible edges in between them. Then the eigenvalues, so that's going to have the minimal eigenvalues, so lambda in this case 2n, the minimal one is going to be minus 1. So that's also going to be a very good expander, but only one-sided. So if you take all the eigenvalues, they're not going to be, then all the positive eigenvalues are going to be really, really small, but they're going to be this minus 1 negative eigenvalue. But if I put the all plus 1 here and the minus 1 here, it'll just switch. So this again, I'm not going to prove this here. That's something you can check on your own. We have this no. In general, in the notes, we have several questions that we leave as homework for you. So these are good to do after the class because they're going to make sure that you understand the definitions. And some of them we're also going to give us as homework, but not all of them. Okay. So now we've seen this spectral notion of expansion and this combinatorial notion of expansions. Another question is how do we connect the two? So there are going to be 2 ways we're going to connect the two. 1 second. So there are going to be 2 connections. So the next topic is going to be connecting spectral expansion and combinatorial expansion, right? So we saw these combinatorial definitions of edge expansion, vertex expansion. We've shown this spectral expansion definition based on eigenvalue that at this point seems completely out of the blue. Like, why would it be relevant? Why would it be related at all? But we want to show that they are related. And we're going to prove two things. So the first thing is going to be something called the expander mixing lemma. This will be a really important lemma that's going to connect the two definitions. Okay, that's going to be the first thing we're going to prove today. Or maybe the only thing we're going to prove today. So G VE is going to be a deregular graph, and let n be the number of nodes. So assume G is a lambda expander. When I write lambda expander, I would just always assume that it's a spectral expander. Okay? Maybe actually no, let's say for today I'll actually write this. Just write lambda spectral expander. Okay, and lambda is small. Okay. Let S and T be two nodes of vertices. What you want to argue that for in expanders, they should be highly connected. Like two large of nodes should be highly connected. What we can prove is actually something even stronger. Not only they're highly connected, but they have roughly the expected number of edges you would see if this graph was like a random graph with the same parameters. So let me write the formula and then explain why it makes sense. Sorry, 1 second. Okay. So I'm going to look, let me define EST, counting the number of edges going from S to T. So I'm just going to say, well, count how many edges I have going first endpoint in S, the second one in T. Then if I take this number and I compare it to what I would see if this graph was a random graph of the same density. So I'll explain what this is the right thing to compare in a second. But the lemma is small. Lambda D square root S T. Okay. So this is a lemma. That's going to be the first result we're going to see. What do we have here? Before we prove it, let's understand what's going on. So EST is the actual number of edges in this graph. What is this other term, ST D over M? Well, think about the graph being deregular, means that every node sees the other neighbors, right? Now think, for example, for a second, that this would be like a random deregular graph. So every node is connected to the random neighbors. Well, what's going to be the expected number of edges you would see between S and T? Assume for now S and T are disjoint. They don't have to be, but let's assume it for a second. So S and T are disjoint sets. So to any node, take any node in S and any node in T. What's the probability they'll be connected in a random deregular graph? I claim exactly D over M. Because S is fixed node in S, it has D random neighbors. So any specific node, the probability is going to be one of these neighbors is going to be D over N. Actually, D over N minus 1, it doesn't make a big difference. I think it's roughly the same as D over N. So if I have S times T possible edges going from S and T, and the expected number of them that's going to be there in a random deregular graph is going to be exactly S times T times D over N. Okay, so this is going to be the expected number of edges in a random deregular graph. Okay. So notice this parameter does not depend on the graph G at all. It just depends on the size of S, size of T, the degree of this graph, and the number of nodes. And what we're saying is that in an expander, in any set S and T, you're going to see roughly this number. Doesn't matter what S and T is. up to this error term, lambda d square root st, which, if S and T are large set, it's relatively small. Yes, this is one way you can think about connecting spectral expansion and edge expansion. In this case, it says that you're going to see roughly the correct number of edges crossing between S and T. So I'm going to spend the rest of the class today proving this, and which I think we might also show you why these spectral notions are useful. Okay, so let's prove it. And then they show the connection between cutting edges and spectral properties. So here are the first facts. So I claim that EST can just be written in the following thing. I'm going to use 1s to denote the indicator vector for S. Okay, so that's going to be the first equality. So why is this true? What is EST? Counting edges between S and T. What is D times AG? Well, remember, AG was the adjacency metric that we divided by D. So now I'm multiplying by D again. This is just a standard adjacency matrix of this graph. It's like 0, 1 matrix. What does it mean multiplying by 1s of the vector 1s and the vector 1t? It's exactly counting all the edges going from S to T, right? So this would be a linear algebraic way of calculating how many edges go from S to T. So now we're going to use this eigenvector and eigenvalue decomposition to approximate this quantity. So remember that AG has eigenvectors V1 up to Vn and corresponding eigenvalues lambda 1 up to lambda n, and V1 up to Vn are an orthonormal basis. So I can take any vector in Rn and decompose it in a unique way as a linear combination of the eigenvectors. So I can write, well, 1s is some combination, some alpha I Vi, right? With just some bases. And similarly, 1t is some linear combination beta I Vi, again, I going from 1 to n. Because any vector I can decompose in this way. And let's plug this into the formula. What is, so we said, what is 1s transpose DAG 1t? We'll just plug this in. So it's going to be 1s is going to be the sum of alpha I Vi transpose DAG, this matrix. And here's the sum of beta I Vi, right? So if you want to just expand all of this together, it's going to be the sum of all I and j, alpha I, let's call this j here, beta j, Vi transpose, there's maybe a d factor here, Ag, Vj, right? Just expanding this quantity. But remember that Ag Vj is just lambda j Vj, because it's an eigenvalue, right? So I can write the same thing as d sum ij, again alpha I beta j lambda j, and then Vi transpose Vj. So that's the inner product between Vi and Vj. And here we're using the fact that Vi and Vj, Vj is an eigenvector. So just go through it, multiply by lambda j. But now, remember, Vi and Vj are orthogonal unless they happen to be the same vector, right? So using the fact it's an orthonormal basis. So because V1 up to Vn are an orthonormal basis, if I is different from j, these things cancel, it becomes 0. So we only get the diagonal term, I equal to j, in which case Vi is 1. So it's just going to be d sum I going from 1 to n, alpha I, beta I, lambda I. right? So already we saw that there is a way, and this is just equal to the number of edges. This is just the same as EST. So there is a way of expressing the number of edges with SNT completely in terms of this decomposition of SNT into these eigenvector bases and the eigenvalues. But now I want to approximate it. So what can we say? Let's look on EST. Let's just divide by D. Let's look on EST. Divide by D. Just so we don't have to carry this D everywhere. So what is this? Well, we said this is going to be the sum of I going from 1 up to n of alpha I, beta I, lambda I, right? Just divided by D. And I'm going to separate the term for I equal to 1. This is going to be special from all the rest. So it's going to be alpha 1, beta 1. Lambda 1 is 1. Remember, in any adjacency matrix, the first eigenvalue is 1, plus the rest, plus the sum of I going from 2 up to n, alpha I, beta I, lambda I. And I'm claiming that this is going to be the main term, and that's going to be the error term. Okay. So really, we can think of the first eigenvector as correspond to the dominant term in this expression, and everything else is small error because all the lambda i's are going to be small. So we're going to bound both of them now. Let's start with alpha 1 and beta 1. What is alpha 1? Alpha 1, what was alpha? Alpha 1 is the inner product in 1s and this vector v1, like the first eigenvector, which was what? 1s and the vector 1, 1, 1, 1, 1 divided by root n, right? So it's just going to be the size of s divided by root n. So we divided by root n because we want this vector to be a unit vector. So alpha 1 is just the size of s divided by root n. And similarly, beta 1 is the size of t divided by root n. So you know, alpha 1, beta 1 is the size of s, the size of t divided by n. And remember, because what we're comparing is to EST divided by d, this is exactly going to be this term, right? If we divide all the terms here by d, then you see it's exactly, we have EST divided by d. We have ST divided by n, which is exactly alpha 1, beta 1. And here if we divide by d, we get lambda root S2t. This is going to be our error term that we're going to prove in a second. Okay, and that's going to be our main term. So we already just saw why the main term is what we get from alpha 1, beta 1. So the next thing is we need to actually prove this error term is this quantity. Okay, but before I'll do that, are there any questions so far about everything I've done so far, or why the main term is what we got? No. And now this might be a bit fast. So I mean, this is why I'm recording this lecture, and this is why we have the notes, so you can look on them like later on. So even if something is not completely clear, it's good to after class go over the material again, make sure you understand what's going on. Okay. So now it's going to be the error term. So the error term is just everything else, right? It's here, the sum of alpha I, beta I, lambda I, except for I equal to 1. So the error term is, let's call this maybe R is the sum of alpha I, beta I, lambda I going from 2 to n. How can I bound it? Well, let's just bound the absolute value of it. We know it's a lambda expander, so all the eigenvalues are very, very close to 0. So it's going to be at most sum of I going from 2 to n, lambda, alpha I, beta I, right? Just because we're just trying to bound it in absolute value. All the eigenvalues, except for the lambda 1, we're assuming they're really, really small, most lambda, right? Remember, lambda I is at most lambda because it's a lambda expander, right? If I is not 1. Just remind me of that. And now we're going to use Cauchy-Schwarz. Cauchy-Schwarz tells you that this you can bound in general. So with lambda here. So you have this inner product in the alpha i's and the beta i's, So it's going to be square root of the sum alpha I squared, square root of the sum beta I squared. This is just Cauchy-Schwarz inequality. Right? So in general, it tells you that if I have an inner product between x and y, just to remind you, it says if I have an inner product x and y, it's at most norm of x, norm of y, for any two vectors x and y. And here we applied for x being the vector whose coordinate are the absolute value of alpha I, and y is a vector whose coordinate are the absolute values of beta I. Okay, what are these quantities? Well, let's see. So here we actually only go from 2 up to n, but to simplify life, let's even bound it from 1 up to n. Why not? It's even bigger. What is the sum of alpha I squared? I went from 1 up to n. What was alpha I? Alpha I was the projection of the vector 1s on the basis vector, eigenvector vi, right? So that's just going to be the sum of 1s vi squared. I going from 1 up to n. So I take this vector 1s, I choose some bases, orthogonal bases, I compute all the projections and I square them. Well, this is just going to be the norm of 1s squared. Because take any vector in Rn, choose any orthogonal bases, compute all the projections and square them, sum them up, you get exactly the length squared of the vector. I mean, it's easy to see that if you think about the standard basis of just a unit that 1, 0, 0, 0, 0, 1, 0, 0, 0, and so on, then just get the coordinates of the vector. But that's true in any vector, because the length of a vector doesn't change if you rotate it. So that's again, it's a basic fact from linear algebra. And what is this vector norm of S1 S squared? Well, 1 is just 0, 1 vector. So this is just going to be the side of S. So I can if I take any 0, 1 vector, indicator for a set S, I compute its projections on some orthonormal bases, and I sum those squares, I get exactly the size of the set S. And similarly, the sum of beta I squared is the size of T. So if we plug this back here, what do we get? We get the absolute value of the error is at most lambda square root S square root T, which is exactly the bound we were claiming to get. And this basically finishes the proof. So again, even if you didn't follow all the details here, maybe the main thing you should think about now is that we can use eigenvalues to show that, at least with respect to edges, expanded graphs have roughly the correct number of edges between any two sets. Okay, and I want to show, just before we finish today, we have a few more minutes. I want to show you one application, one nice application. So let G V E be a lambda spectral expander. And then I'm going to show that such a graph cannot have very large independent sets. So let S in V be an independent set, meaning a set without any edges in it. Then the side of S is at most lambda size of V. So if lambda is very, very small, expanded graphs do not have large independent sets. Okay, and I'm going to show you the proof is going to be just basically a one-line proof given this expander mixing lemma, but maybe this will help you to understand the parameters. So let's see the proof. Well, because S is an independent set, it has no edges, right? So the edges between S and itself, there are no edges by definition. So let's just plug in. So plug in S, and then also choose T to be S in the expander mixing lemma. So what are we going to get? Let's go back. So we had here this EST, which is 0, right? So 0. minus the expected number of edges. So again, it's going to be a d-regular graph, let's say. So d s squared over n, because t is the same as s. And that should be smaller than lambda d. Well, square root st is just the same set of s. Now notice also d cancels. D is not really important here. So what do we get here? We get the side of s is smaller than lambda n. N is the side of v. That's it. That's a proof. It's just a one-line application, but you already see it shows something very non-trivial. It shows that if I have an expanded graph, it cannot have large independent sets. And if you study any type of graph theory, it's usually hard to prove that graphs do not have large independent sets, and it is computationally hard to find the side of the largest independent sets or to approximate it. But somehow being an expanded graph allows us automatically to show that. So you should think, if you're coming from a more of, let's say, a CS perspective, you think about spectral expansion as some type of expansion that is easy to compute. We have efficient algorithms to compute eigenvalues and eigenvectors of graphs. And this could be used to certify various aspects about graphs that might be hard to do combinatorially, like having large, not having large independent sets. Okay. So this is it for the expander mixing lemma. And for this one application, there is another application that we're going to leave to you as homework, which is this other application. I mean, I'm going to tell you the application. I'm not going to give you the proof. So again, let G VE be a lambda expander, spectral expander. Let's define the diameter of G to be the maximal distance in G between two nodes, right? So take any two nodes in your graph, ask what's the distance between them, what the shortest path distance between them, and take the two furthest away nodes. This is called the diameter of your graph. So I'm claiming that, let's say lambda here is at most a third for this specific proof to work using expander mixing lemma. So assume this. Then the diameter of this graph is actually very small. It's order log n. Again, n is always the size of it, right? It's always going to be the case for us. So the claim is in an expander, the diameter is very, very small. So even though it has n nodes, you can go from any point to any point using at most log n jumps. So one of your first homework questions is going to be prove this using the expander mixing lemma. So that's a nice challenge question. Later on, we're going to see, but if lambda here is very, very small, somehow we don't get any better bound. I just want to point that later, well, next week, we're going to learn techniques, slightly more advanced techniques which would allow to prove a better bound. But if lambda is very small, you get a better bound to prove that actually the diameter of G is order log n over log 1 over lambda. So if lambda is sub-constant, you actually get even better bounds of diameter. But for us, but if we put this weaker bound just with the expander mixing, that's a nice challenge. Okay, so I think we reached the end of the class today. So let me just recap what we covered today and tell you briefly about what we're going to do next lecture. So we defined two combinatorial notions of expansion, edge expansion and vertex expansion. We sort of analyzed them for some simple cases like the complete graph. We saw examples of sparse graphs that are good expanders, like this x plus 1, x minus 1 is 1 over x, the cycle graph. But the proof is complicated. But that's really going to be our main focus. Sparse graphs that have good expansion. But it's not clear how to prove this directly. So the way that we know how to prove this is by connecting this to spectral expansion. and proving that these graphs have very good spectral expansion, and then showing that this actually implies that they have good edge expansion and good vertex expansion. So what we saw today was one direction, showing that if you have a graph with a good spectral expander, then any two sets of nodes have roughly the correct number of edges between them. If the graph was like a random graph with the same density. What we're going to see next lecture, next is going to show it, is something called Chigger inequality. This is giving us a very sharp connection between spectral expansion and edge expansion of graphs. So what we're going to see on Thursday is exactly this connection. So maybe I just state the theorem and then next is going to prove it on Thursday. So Chigger theorem or Chigger inequality. So it connects two things, the second eigenvalue and the expansion. So it says h of g, so the edge expansion of g is smaller than root 2 1 minus lambda. Okay, so it gives some relatively tight connections between the gap from one of the largest eigenvalue and the spectral expansion. And in fact, to prove that, you don't even need to one-side expansions are enough. So actually, if you put in lambda 2, it would even be correct. But that's a minor point. So again, Max is going to repeat all of this on Thursday, and we're going to see the proof. So that's it for today. So before we finish, are there any questions?
Just to make sure, in the second inequality in the expander mixing lemma, did you add just the first term, alpha 1 plus alpha 1 times beta 1?
Yes. So when we go up here, and go back, the main term was just alpha 1, beta 1, lambda 1, but lambda 1 is 1. So it's just alpha 1, beta 1.
Okay.
So in general, we'll see that a good way of analyzing different quantities about graphs is identifying the main term, calculating it, and then proving that everything else behaves like sort of small noise. It doesn't contribute much to the actual calculation. So that's a very common, a very useful technique, not just in graph theory, but in many other areas, where we have some type of pseudo-randomness, like for example, for expanded graphs. Okay. Any more questions?
I have one question.
Yes.
Can you explain the probability space of a random regular D graph?
Yes. So I mean, it would be slightly easier to, instead of doing that, okay, let me talk about it for a second. So we can talk about, okay, let me just look here. So let's talk about the random graph. So what's called the GNP graph. So GNP, random graph. That's going to be a graph whose vertices have n vertices, and its edges are sampled independently and randomly. So each edge, each possible edge is chosen independently with probability p. Okay. So this graph is defined by two parameters, n and p. So n is the number of nodes, and then you look at all possible and choose two edges, and each one you choose it to be in this graph independently with probability p. So I'm saying, so for example, so if you want this graph to have expected degree d, you want to choose p to be d over n minus 1, right? If p is d over n minus 1, then, so if this is the case, then the expected degree of each node is d. Why? Because each node has n minus 1 possible edges. Each one of them is chosen probability p. So the expected number of edges is going to be p times n minus 1. So if I choose p to be d over n minus 1, I'm going to get exactly d. And now what was this? Now we're going to approximate p to be something close to d over n, just so that it's slightly easier to write. So what is a expected Let's look at the number of edges between S and T. Let's say S and T are two sets of nodes. Okay, let's say this joint for now. So what's the expectation of this number? So we're going to go over all possible nodes, S in S, T in T. It's going to be the probability that ST are in our edge set, right? By linearity of expectation. Right, we go over all possible edges and ask 1 if they're there, 0 if they're not. So it's just going to be the expectation is just going to be the probability that this edge is in this graph. So what is this? This is exactly S times T times P.
Okay.
Right, which is exactly ST D over n minus 1. But you know the difference between divided by n minus 1 and divided by n is even a much smaller error term for what we care. So this is how come we got this. I told you that this main term is really corresponding to random graph. So our main term in the expander mixing lemma, in the expander was STD over n, which is essentially the same, right? The difference is like much smaller. And then the error term anyway that we got.
Okay.
Okay. Any more questions? So I think if for some of you, maybe you feel like, you haven't done any linear algebra in a while, or some things are not so clear, then it could be good for you to go over some, maybe some basic concepts in linear algebra before you come to the third. This is like what we are going to use linear algebra a lot. This is the stuff that you learn at the basic undergrad class, eigenvectors, eigenvalues, and things like that. So I'm assuming you should know these topics. Okay. So maybe let's finish for today. And again, we're going to post a video later on the website, and we're going to see you all on Thursday. Okay, see you.
All right, thank you.